Hello. In this video, we're going to talk about measures of variation. And by variation, we kind of mean how spread apart is our data along a horizontal axis. One of those measures we can use is what we call the range. It's the simplest of these measurements, and it's just going to be the difference between the largest and smallest of these measurements. So if we look at this example, a botanist records the number of petals on 5 flowers. We want to look at the range of this data. The largest data point is 14. The smallest data point is 5. That means the range is just 9 units long. The range in and of itself may not be a good enough measure of variation, right? Here we have two charts. They have the exact same variation. They go from 1 to 8, right? The data points are 1 to 8, but clearly the distribution of them is different. This chart here is clearly more focused in the center, whereas this upper chart here is kind of more spread out. We would call this a more bimodal distribution because it kind of has uh, kind of two peaks right there. So we kind of need another way to measure excuse me, measure the variation of data relative kind of to itself. And the way we do that is by variance or standard deviation. And I prefer to define things in terms of variance first, um, because I think the formulas are a little bit easier to keep in our heads for variance. So the variance is a measure of variability that uses all the measurements, right? And it measures the average deviation of each of these measurements from the mean. And that's the key, that it doesn't just take the highest value and the lowest value. It takes every single data point and compares it somehow to the mean of the set of data. And we get two different variance formulas, one for population and one for sample. If we have a population or if we have a sample set of data, they're almost identical. We use slightly different variables. So a variance of population we use capital N to denote the number of items in our population. This variable we call sigma. It's the lowercase letter sigma in Greek, and it's the sum of the difference between our data points and our mean squared. We're going to add all those up, and then we're going to divide by the number of data points in our population. The variance of a sample, on the other hand, is almost that exact same formula. We use S to denote the variance of a sample, S squared. Remember, X bar is the mean or average of a sample set of data. We're still squaring this difference and then taking the sum. But when we do a variance of a sample, we now divide by n minus 1, right? It's a slightly different thing. And again, formulas are provided for us, so we'll be okay. So let's just kind of do an example. So we want to find the variance for the sample set of flower petals that we had in the previous example. So we have 5, 12, 6, 8, and 14. So if we're going to kind of use this formula, because we're told we have a sample set of flowers, the best thing to do, we can just kind of ignore that column. This is the only way I could draw tables in this set, in this typesetting. I really kind of think it's a good idea to set these up in terms of a table like this, where our first column is going to be my data points. My second column is going to be the difference between the data points themselves and the mean. The third data point, or the third column, is going to be the squares of that second column, right? Because again, what we're going to do is we're going to basically build up this numerator, right? I want to get all of these xi's minus x bar squared. And then once I have all of them, I can add them up, and the column is going to help us do that. Another thing the column is going to help us do is we want to find the mean. We don't quite have the mean. So what we can do right down here is kind of come up with the mean, find the sum. So if I add up that whole column, 5 plus 12 plus 6 plus 8 plus 14, I'll get 45. I want to divide that by 5. because there's 5 data points, and I'll get 9. And this is going to be my mean. And so for this first column, what I'll do is I'll take 5 minus my mean, which is -4. 12 minus 9 is 3, -3, -1, and 5. We just kind of do that all, keeping the signs in our mind. This next column here, this final column, we're going to square each of these data points. And what's nice about squaring them is what happens if I take a -4 and square it, I'm going to get a positive 16, and then a positive 9, a positive 9, a positive 1, and a positive 25. This whole column should always contain positive numbers, right? No matter what this column is down here, I'm always going to square it, which will yield positive numbers. And why this is helpful is down here, I can add up this whole column, and that's going to give me the numerator of my variance formula, which if I add all these things up, I'm going to get 60. So when I go to find my variance, s squared, right, I want the sum of my xi's minus x bar squared all over n minus 1, so s squared. This is what that whole column helps us find. That top part is 60. I have 5 data points. I want 5 minus 1. That's 60 divided by 4. And if I compute that, I'll get 15. That's how we compute the variance. Standard deviation is kind of the one we're more familiar with. I tend to not like to teach this first because standard deviation is really just the positive square root of our variance, right? So the variance of a population is just going to be sigma. It's the square root of sigma squared. And the standard deviation of a sample is just going to be the square root of s squared. So for our example, the standard deviation is going to be the square root of 15, because that's what our variance was. And if we do that, we'll get 3.873, kind of rounding to 3 decimal places. That would be our standard deviation. So I tend to like doing variance first, because just finding standard deviation is just one more step. It's just finding the square root. So just some facts about standard deviation. Again, so what does the standard deviation and in turn, what does the variance really tell us? They're the measure of how much the data values kind of change from the mean, right? We talk about a measure of variation. We need to know what we're measuring that against. What are we varying in relation to? And for the parameters and the statistic variance and standard deviation, that value is the mean. And so because of that, it's really just a measure of kind of total distance. And so the standard deviation and the variance are never going to be negative numbers. They're always going to be positive, right? Variance needs to be positive because I need to take the square root of it to find standard deviation. And we can't take the square root of negative numbers. It could be 0, but that's extraordinarily unlikely. The only time it's 0 is when all of the data values are exactly the same. And so what can we glean from this information? That really large values of S are going to indicate a really large amount of variation. The larger the variance or standard deviation is, the more likely our data set is to be kind of spread apart relative to its mean. What if our data set is kind of large? Do we have to find the standard deviation of an extraordinarily large data set, hundreds or thousands of pieces of data? Well, you having something like Excel or SPSS or any of these statistical software packages, they kind of help us compute it. But if we're trying to do this by hand, we do have a shortcut that's called the range rule of thumb. And it's just a crude way to kind of estimate the standard deviation. And at its core, the standard deviation is going to be somewhere about approximately the range divided by 4. One of the reasons we use standard deviation, whether it's S or sigma, is because it helps determine when data points have significance, right? Whether they're significantly high data points or significantly low data points. They are going to be the things that really kind of help us encapsulate what's an unexpected data point to see and what's an expected data point to see. So data is significantly low for values that are 2 standard deviations lower than the mean. That's what this means. 2 standard deviations below the mean. They're significantly high if they're 2 standard deviations above the mean. And they're not significant. These values are not significant if they fall in between these 2 standard deviations. And so we kind of get a nice little picture like this. Like if we have the data points on this kind of horizontal axis, here's the mean of the data set. All of these values that kind of fit between these two, these are what we'd call not significant. We would expect most of the data to fall really between these 2 standard deviations. If we get a value that's 2 standard deviations above, we call that significantly high. That is kind of a significant value to get. Likewise, if we get something below 2 standard deviations, that's a significantly low value that we can get. And we can know a little bit about this. And if we know what type of distribution we have, if we kind of know that the data should have a basic shape, we can improve upon this idea of significance to a bigger degree. So a normal distribution is what we call a bell-shaped curve. And this is kind of what we would expect for a normal distribution. Right here is our mean mu. It is, it is the value directly under the mound. And what this helps with, knowing that we have a normal distribution, this allows us to have what we call an empirical rule. And the empirical rule says, given the distribution of measurements that's about normal, this interval of mu plus or minus sigma, this is one standard deviation within the mean, is going to contain approximately 68% of our data points. So if we have mu here, and we have right here mu plus sigma, and here mu minus sigma, we're going to get about 68% of the data to fall between there. And what's nice about this is this thing is completely symmetric, which means it looks exactly on one side as it does on the other. So if it's about 68% on both sides, I'm going to get about 34% and 34% to combine to 68%. The interval mu plus or minus 2 sigma, so that's 2 standard deviations, contains approximately 95% of the measurements. And if we look down here, 3 standard deviations within the mean, so mu plus or minus 3 sigma, is going to contain approximately 99.7% of the measurements. And we do kind of get a nice little graphic that goes along with this, right? Here's our mean. In between one standard deviation is that 68%. But what this graph does is it breaks it down in half, so 68%. And if we cut that in half to the left and to the right, they should be equal parts, so 34 and 34%. Between 2 standard deviations should be about 95% of the data. And if we added all of these numbers together, we would get about 95%. Within 3 standard deviations, we get about 99.7% of the data. And if we added up all of these numbers, we would end up getting about 99.7% of the data. What if we don't know our distribution, right? Are we out of luck if we don't know that it's a normal distribution? We have a theorem called Chebyshev's theorem. And it says, given a number k greater than or equal to 1, and a set of n measurements, at least 1 minus 1 over k squared of the measurements will lie within k standard deviations of their mean. And this is powerful. This is a really powerful theorem because it is independent of the distribution that we have. It will work all of the time for any distribution. So what's also important is it doesn't matter what the mean or standard deviation are. It just says if I have a set of n measurements and I want to know how many standard deviations away I want to be, I can get a lower bound of the percent of data points. So here's an example. How much of the data must lie within 2 standard deviations of the mean? And if I look at this, it's 1 minus 1 over k squared, 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4. Or if I compute that, that's 75% of the data. So 75%, at least 75% of the data must fall within 2 standard deviations of the mean. So again, if we're talking about 1 standard deviation, it's going to be mu minus sigma or mu plus sigma. If I'm talking about 2 standard deviations, it's mu minus 2 sigma as our lower bound, mu plus 2 sigma as our upper bound. The nice thing about Chebyshev's is the only condition on k is that it has to be greater than or equal to 1. So it could be a fraction. What if I wanted 3.5 standard deviations? All I would do is just do mu minus 3.5 sigma and then mu plus 3.5 sigma. So let's look at kind of really the 2 types of problems we might want to solve for Chebyshev's theorem. So if the mean and standard deviation of a set are 55 and 12 respectively, so I know, okay, this is my mu and this is my sigma, what percent of the data must lie within 3.5 standard deviations of the mean? And then what are those bounds? Well, we can do that. If I want to know what percent of the data, I use this result, 1 minus 1 over k squared, and I'm told what k is in this case. K is that 3.5. 1 minus 1 over 3.5 squared. If I compute this, I'll get 0.918, right, using a calculator, which for us, we can turn into 91.8% of the data. If I want to know my bounds, my lower bound, my lower is going to be mu minus 3.5 times sigma. That is 55 minus 3.5 times sigma, which is 12.3. And if I compute that, I will get 11.95. And if I want to look at my upper bound, I get mu plus 3.5 sigma. I get 55 plus 3.5 times 12.3. And if I compute that, I get 98.05. Those are my lower and upper bounds that relate to these numerical bounds. So in this example, we're kind of given the k value, and we want to find our lower and upper bounds. In the other type of problem we could solve using Chebyshev's, we might be given numerical bounds with a mean and standard deviation and want to find k. So suppose the average score on a math exam is 71 points with a 9-point standard deviation. What percentage of people score between 59 and 83 points? This question at its core is saying find k and compute 1 minus 1 over k squared. And so to do that, what we're going to do is we're going to look at one of these 2 bounds. And if we kind of look up at the formula for these bounds that we've had, notice that 1 standard deviation below and above, the only thing that's different is the sign. It's the mean minus the standard deviation or the mean plus the standard deviation. Same thing for 2, the mean minus 2s or the mean plus 2s. And so what that allows us to do is pick one of these bounds, let's say 83, and think about that as the mean plus I don't know how many standard deviations. times sigma, right? That's what we want to find. In this case, we're finding that K value. But what we're given in this problem is we're given the mean and we're given the standard deviation. So I can refine this equation to be 83 is equal to 71. That's our mean. K, I'm still unsure of, and my standard deviation is 9. Which, if we start to solve for K, I'll get 9K is equal to 12, because I'll take 83 minus 71, and then I'll get K is equal to 4/3. And this is perfectly fine. Our condition for Chebyshev's was that K was greater than or equal to 1. In this case, this K is greater than or equal to 1. So we can compute now, right? We've done that. We can compute our 1 minus 1 over K squared. 1 minus 1 over, I'll get 4/3 squared. And we want to be a little bit careful plugging this into a calculator because of the fraction in the denominator there. If we do that and compute this, I'm going to get 0.438, or if I convert that to a percentage, I'll get 43.8%. And so we can say with certainty that at least 43.8 of the students scored between 59 and 83 points. Hopefully this was helpful. If you have any questions, please let me know, and I'll talk to you next time.